So we're gonna, our last example will be axial and flexure together on a CMU masonry wall. The example, I've decided to print you out or give you my copy of the solved example, so that's available on the Canvas site. And that's because, it's not an unbearable example, but it's a little bit complicated in that there's a lot of checks. And so the problem is also just a blank page in your notes. So go ahead, you can just put the full example behind that. You can print it or put it on your electronic device or whatever you want to do. So I'm going to go through this, and you have this copy. Go ahead and make notes on it in whatever form you want, electronic or on paper. There will be a problem like this on the final exam, so you should be able to go through this. Um, if you and watch this whole video, because I'm going to point out things as we go along, and it's going to be important for you to be able to do your homework, and it's also going to be important for you to be able to complete the exam. So let's go through this. And the basic problem is a wall, and it's shown here in, so I'm just going to highlight this piece as we go along and try to show you where things are coming from. All right, so this is going to be this exterior western wall is the one we're going to be designing. There are timber, glue lambs or something, or these blue items here in the roof system, and it's 6 bays across. It's 55-foot width of wall, so in this direction. And the way that the load from the roof is getting to the wall is if I look just outside to the west here, I've got an axial load that's coming down, carrying all of the load from the roof pieces, and I'm going to give you that load for live and dead from the roof, and it's at an eccentricity of 8 inches from the center of the wall. So it's on the same side that the wind will be coming from. So both the wind and the load from the roof are going to produce the same kind of moment. All right, so I've got several things going on here. What I'm going to want to do for this problem is essentially select the steel for the given wall. We're going to use the modified method 3 for this, which is the most common one. It will be a tension controlled section, and we're going to assume it's basically simply supported top and bottom, and it has a height. Did I give you a height here? Height of 20 feet. Okay, so the height equals 20 feet. And I've written that down here somewhere. All right. So because of this, we get to use a full height since it's simply supported for the buckling piece. The wind load is going to cause a buckling like this. That's pure moment induced. The self weight of the wall itself is axial load only because it's through the centroid. And then this piece that's coming from the roof members is offset by 8 inches. So it's going to be P times E, which will give me a moment contribution. Right? And this is also it's the same thing. It's going to further bend the wall in this direction. But it's also got an axial contribution, P. Okay, so what does this look like? And note that the self-weight of the wall, if I was at the top of the wall, I don't feel any self-weight. As I get to the mid-height of the wall, I have about half of it, and then by the bottom, I have the full thing. So we're also going to have to decide where's the critical point. Is it at the top, the bottom, the midsection of the wall? And I'll talk you through that. Okay, so pause this video as you need to. You want to watch the whole thing. Again, this is going to be on the exam, and you're going to have homework on this to practice. The homework will be probably pretty similar to this, so you can practice this since I wrote all this out for you on the example problem. All right, so what do I have? I have a vertical load of the self-weight of the wall, right? I've got a vertical load from the roof, live and dead. Lateral loads, in other words, that are going to cause the moments. I've got a moment due to wind. I've got a moment due to the roof, live and dead, right? That's this moment, P times E moment of the roof piece. Okay, so I've given the following loads. The roof dead load is 14 pounds per square foot. The roof live load is 20 pounds per square foot. I've got an eccentricity of 8 inches. And note that the tributary width, if I'm giving pounds per square foot from the roof loads, is on this edge wall is 12 foot. So they're 20 foot, 24 foot bays, so that's a 12-foot trib width. Okay. So if you start seeing magic numbers come in there, look for your tributary widths, your eccentricities, etc. The wind load is a surface loading of 22.2 pounds per square foot. All right, so all these loads are in pounds per square foot, so we're gonna have to multiply by the section width, depending on which direction. It's a 8-inch CMU block, medium weight. It's solid grouted. Now remember, for what we're doing, solid or partially grouted, that's not changing anything as far as the capacity. It's 20 foot tall. Here's the height. And we're going to assume the steel is in the center of the wall. And it's got an F prime M of 2000 and grade 60 steel. Okay, so first of all, let's figure out where along the length of the wall, if we assume top and bottom simply supported, or you can think about it on its side as simply supported if that's easier for you to think of the moment diagrams, right? But at the top, if we look at the moments we have, we've got the wind one and we've got the roof one. So the roof eccentricity piece is going to end up with a concentrated, whichever direction would I say? Okay, so a concentrated moment, and I may have flipped these, it doesn't really matter which side, the shapes are the same. So I've got my concentrated moment um, at the top, right? So that would look something like this type of moment at the top or the other direction. And that type of moment does this, right? And then the normal moment that we're used to from wind load does this. And so that's what I'm showing here is the two of these together. And you can tell at the bottom, there's self-weight and whatever axial, but there's no real moment. There's moment maximum of the offset at the top, and there's moment maximum of the moment due to wind at the middle. There's half the eccentricity moment at the middle. So we would check to see which one of those, adding those two together, is this or is this plus this the maximum moment. We're going to assume for this problem, because I'm telling you to, that we're going to assume that we're going to do this all at mid-height, so h over 2 controls. On your exam or homework problem, I will say check or assume that mid-height or wherever I'm going to say assume that controls. So if I found out that the top controlled um, that piece, there would be no wind piece to that. Okay. All right, so first thing we got to do is figure out, and the loading part here right at the beginning takes a little time. Once you have visualized exactly and draw yourself these types of drawings, where everything goes, make sure you've got things going in the right direction. So in my case, the moment due to wind and the moment due to the offset are going in the same direction for this problem. They add together. You just have to be careful on other cases. If it's a building where the wind on the wall could come from either side, note that. Just make sure whether you're adding or subtracting things. These are all added. So our applicable load cases for this are load case 1, which is the D plus 0.6 wind, load case 2, and load case 3. Each of those have the dead wind, and we're using the roof. We don't have rain or snow on this one. Okay, so it's this case. All right, so there's some portions that we go through where it'll ask you for the P max or the M max, and those are the greatest ones from these cases. If it is, but we will each, when we decide how much steel, and when we do our final checks, we need to check each load case. All right, so let's just start out by making sure we've got everything ready to go. So my W from the dead load and live load of the roof are here, multiply by that 12 foot, okay? That's the tributary width from the loading from the roof. And then I've got my self weight, okay? So the self weight, if I'm looking at the center of the wall, it's going to be over 2, okay? And I get this pounds per linear foot. because we're doing pounds per linear foot of wall, right? Of wall. For moment, um, I've got the same basic idea, pounds per linear foot of wall, 8 feet, 12 inches per foot, times 1/2, or 8 feet, 8 inches, right? So 8 inches. So the moment here for these two is P times E. Okay, so I took my roof P in both cases times the eccentricity, 8 inches, converted units, and I get 56 pound-feet per foot of wall, per pound-feet per foot of wall. Moment due to wind, okay, that's the one that we just looked at here, WL squared over 8. So I put my wind load in there, got the L squared, in this case is the height, over 8. So the biggest stuff as you start to get into doing walls, particularly, and 3D things, is you're going to solve in 2D, but you got to think in 3D, is all these formulas we've used forever, WL squared over 8. What's the length? In this case, the length is the height of the wall. Okay, so you just have to think clearly, draw as many sketches as you need. That's the toughest part of the problems, I think, is the setup. Using the equations is not as big a deal. Okay, so if I go through and figure out for each of these cases, okay, take those axials and moments, and I'm going to keep them as separate axial and moment, because remember, this is an interaction between the two. I'm going to go ahead and put the load factors in, and these are the 3 load cases. This is the P and M for each one of those load cases. Okay. Unless you've got a case where both, well, honestly, you should check all 3 cases because the interaction diagram does weird things. It's in different shapes. It's hard a lot of times to guess, and you're typically going to have one that has a bigger P, one that has a bigger M, and then, like we have in this case, one that doesn't have the biggest P or the biggest M, but is kind of the second biggest in those. So, in fact, I was trying to guess straight off the bat and I was thinking LC3 probably won't control because it's got such a low P, but it's got the second highest M combined with that P, and you just don't know where it's going to be. Remember, we have that weird interaction diagram. You actually have to just calculate them out. Okay, so it turns out actually that this one does control. We will use the largest p-value when we need to put in a p-max, and we will use the largest moment value when we put in an m-max. So we're going to end up using loads from all 3 of these load cases. All right, now we're going to follow the modified 3 method. Okay. First step is determine whether it's tension or compression controlled. I'm going to give you tension controlled ones on your homework and on your, which is more typical, and on the exam. So if you do this check and you find out you're compression controlled, if I ask you to do the check, proceed as if it's tension controlled. It just means somebody messed up somewhere. So we're going to check this, but you can only use modified method 3 for tension control. If it's compression controlled, you have to go back and just use the standard method 3. All right, but this is the case that's going to cover the most choices. And you have examples for every method in that engineering handbook from the Masonry Society. All right, so first thing we do is take the maximum moment. Okay, so that was the 722 pound-foot per foot, and I need to check that and see if it is less than or greater than the balance moment, right? Because if I'm on, I tend to draw my interaction diagrams like a concrete one. It kind of depends on the thing. So if I'm on a certain cutoff point, it's tension controlled, and another cutoff point, it's compression controlled, right? So compression, tension controlled, basically. And that's what I'm trying to find is for the balance moment, if I've got a bigger or smaller moment than that case, and that tells me that I'm in the tension controlled region if I'm less than that. Okay, so there is an equation right here for balance moment. This is in your notes or in the engineering handbook. You can follow that guy along. The difference in the example, well, follow that along to get the equations. And remember, if this whole term drops out, if I'm going to put, so here's what I'm doing, right? I've got the reinforcement, the the buckling is in and out of the paper. So if I'm looking down, it's kind of like this. And that means that this is my D, right? Or I'm sorry, that's my height of the section. This is my D of the section. And you can see that D in this case of the section, or the D1 of the section is half of L, if L is the height. Okay, so D is that value. I'm going to D1 or D, whatever you want to call it here. D1 in this case is talking about D. So if that is L over 2, this whole term drops out. And that's the case for any of these. And you're only going to be given ones where it's in the center. It doesn't make sense when you're doing this type of buckling to try to put it towards the edge because you're going to want to, a lot of times it need to be symmetric, but there's just also not that much wiggle room. And the chances are it's going to get put on the wrong side if you try to specify that. So you put it right in the middle, which knocks out that term because you get L over 2 minus L over 2. Okay, if you go back into the handbook or the notes, we talk about that these are the values for K and J balanced for CMU. We have per foot of wall length, so that's the B value in this moment balanced equation. We just talked about D is 3.8125. Now, moment balance, I can then run through that calculation. Don't leave off the square here, so it's D squared. And I will get 1828 pound-foot per foot. So really watch your units, which means that the max moment of 722 is less than the balanced, which means it's tension controlled. So I can continue on. If it's compression controlled, I have to use method 3, the non-modified version. So step 2 is just basically doing the comparison. Step 3 is to estimate how much steel I'm going to need. So this equation is also in the handbook. So for masonry, the amount of steel required is going to be the moment minus 40% of axial times L over 0.9 F sub S D. So let's look what we got here. We're going to have to check each load case. So I'm using Pmax or Mmax when necessary, but when I'm actually solving for the required steel or checking the final calculations, I need to check all 3 load cases. So you can see that a spreadsheet's going to help a lot, or if you're working for a firm, they may already have spreadsheets set up for some of these computations if they do a decent amount of masonry. It's also not that bad by hand. All right, so load case 1, I just copied back down what axial moment we have, put that in the area of steel required equation. I got 0.053. Same thing, load case 2 with its P&M, 0.036 inches squared per foot of wall. And finally, load case 3, I got 0.061 inches squared per foot of wall, which happens to be the largest one. Okay, so that's the controlling area of steel. So I'm going to pick the number of, or the type of number of bars based on that area of steel required. So I'll try number 5 at 48 inches, and then I can go up or down depending on how that lands. Remembering that I want a multiple of 8 for this CMU. So a number 5 is 0.31. I'm going to put it every 48 inches, which gives me 0.077 per foot of wall of inches squared per foot of wall. And that is greater than the required controlling area required of steel. Okay, so now I have my design. That's going to be my answer if everything checks out. So now, still have some checks to do. I need to check the axial demand and allowable, or the required and demand, and the same for the M. So first off, FA, little fa, less than or equal big FA. I'm going to use the maximum P to determine that FA, and that was 1128 of the 3 load cases, divided by the area of 1 foot of wall, so that's the height of the wall, 1 foot of wall, and I get 12.3 psi. All right. I now need large F sub A, and that depends on wall slenderness. So remember, there's 2 equations, H over R greater than or less than 99. So H over R is, in this case, the height of the wall, 20 feet, converted to inches, And then R, I can look up the radius of gyration or just calculate it from I over A, which I get 2.2. Sorry, I shouldn't probably have units on that guy. 2.2, and I get an H over R of 109. That's greater than 99. So I use this equation. And there was another term on this equation, but remember we're only counting the masonry piece for axial. Okay, so this is the full equation. You can look back to find the one for less than 99 if you end up using that one, both in the handbook and the notes. Plug in there, since this is H over or R over H over R just goes on the bottom, and I get 206 psi, which is much bigger than the required, and so I'm okay. Now I need to check the moment versus the moment allowable. All right, so moment allowable is this equation. And we can't just knock this out because we have KD over 3 here. It's not L over 2 or D. The first thing before you go into that equation is just verify that your FM or your axial plus bending or your axial plus steel part is less than or equal to the amount provided by the masonry. I'm going to need K and J and some of these terms. So the shortcut here is to go ahead and figure those terms out and use the equation F sub M is K over 1 minus K, Fs over N, and that's, of course, your E ratio, right? Your modular ratio. All right. And for the masonry and the steel grade we've been using, that'll end up being 16.1. Okay, so let's start and go through each load case because it'll be different for each one. Start out, let's check this FM thing. And so I need K. I'm gonna also need J. All right, K, this looks, it's basically the quadratic equation without the over 2a. So to know where this comes from, go back over to the handbook and they derive this on page 170. So it's just because they get a long equation with multiple terms and you need to solve for k. The a value in that equation is here, the b value is here, and the c value is just the opposite of b. All right, so I'm going to go in. Note that the t in this is per foot of wall. All right, every other term we pretty much have used here. F sub s is this guy. All right, so if I go in my k equation, negative b, b squared, since it's minus 4 and c is minus, I just switch it to plus, okay, and I will get a k of 0.24. My FM value I then have, and I know that my FM value, oops, I missed something here, I think, 0.45 FM. Should be a 0.45 here, sorry. I'll change that. I think by the time you get this sheet, that'll be changed. Okay. And so I find out that I'm okay for that check. All right, now let's go ahead and find the other terms I need for the moment allowable. I need J, which is 1 minus K over 3. Plug everything into the moment allowable equation, and I got 995 pound-feet per foot. And for load case 1, the actual was 722. So with my steel that I chose, I'm good on that one. Then I go ahead and do the same thing for each of the other 2 load cases. And I found out those both work. So all those checks worked out. And I can use my number 5s at 48 inches on center. So I've lined out, other than this last 2 where you just repeat those checks, I have done each piece of this problem and tried to document it as I went along the way, show you what steps we're on. So use this when you're doing your homework, and that'll be a good practice for the exam. All right.